In this seminar, the consideration of medical imaging fusion as an alternative to current technologies will be discussed. The problem description will detail what our design aims to solve. Next, the performance criteria will be outlined and will include information of the project system requirements. Project requirements will go into detail on both the functional and non-functional requirements of the design. Finally, environmental, social, legal, and ethical factors regarding the design process, manufacturing, implementation, and utilization of the design will be discussed. Our design aims to provide a solution to problems caused by current medical imaging technologies. Current medical imaging technologies, although efficient, are limited in providing clear visualisations of patient conditions. These inaccuracies in current techniques lead to missed or incorrect diagnoses that are detrimental to patient health and cost the Australian health sector greatly. It was determined that the design of a multimodal imaging fusion technique would reduce the need for multiple scans, reducing the likelihood of high patient exposure to ionising radiation. Further, three-dimensional fusion computed tomography scans will reduce scanning times and thus exposure time. In order to determine the design, the engineering method was used to conduct an evaluation of two fusion methods against a series of success criteria. Additionally, environmental, legal, ethical, and social impacts were evaluated.
Through analysing our chosen issue and applying the engineering method, significant research was conducted before choosing a solution. Some of these potential solutions included using artificial intelligence, wearables, or spatial fusion to improve the accuracy of medical imaging. However, after evaluating potential designs against the success criteria, it was determined that multi-resolution fusion was the best option to pursue for our requirements, in comparison to a spatial fusion alternative. The design consists of two or more imaging devices which then deconstruct the images produced and finally fuse them into one. The infrastructure may either take an HIS-based fusion approach or the pyramid method. For both methods, separate cloud storage systems must be put into place to manage storage and security. The system's processes must be monitored throughout the entirety of the imaging process.
Performance criteria based on Australia's health needs involve the development of treatments, solutions, and prevention strategies to further assist in both physical and mental health. More importantly, the implementation of this technology is required to be of use amongst the stakeholders, which are the Australian government, medical imaging businesses and manufacturers, patients, and staff members. Specifically, the functional requirements of medical image fusion should address the common misdiagnosis present in the medical imaging industry, such as improved resolutions, data storage, and image distortion prevention. In particular, the high resolution of multimodal images will assist in optimizing the accuracy of diagnosis. The addition of this method in radiology services can also help generate wider economic benefits as requested by the Australian government. Along with this, several non-functional requirements must be taken into account. These specifically include cost, usability, maintenance, and efficiency. The cost of production should be affordable, such that medical image fusion will be readily available across hospitals, radiologists, radiographers, and specialized technicians will be trained on the usability of these machines, and regulated maintenance must be performed by qualified technicians in order to prevent potential errors. Hence, with these specifications and requirements in mind, medical imaging fusion can provide many benefits for all users associated with this project. Functional system requirements relate to performance and execution of the project. The implementation of this design has the aim to increase the resolution and overall quality of current medical scans. This has the effect of increasing the accuracy of diagnosis, with the aim of reducing the rate of perceptual errors and interpretive errors. The resolution parameters can be measured through comparison checks with differing imaging scanning techniques. The objective of this increased resolution is not only to have higher pixel per inch, but to also have increased clarity on the focus of the scan, such as the concerning region of the patient. By considering these factors, a comparison between sample images from both imaging fusion and current imaging techniques can be conducted, and the success of the parameters can be determined. The non-functional system requirements include the cost, efficiency, and maintainability of the design. Medical image fusion ideally should be implemented across a large number of medical facilities, and therefore an affordable cost both to buyers and patients is a key aspect of the success criteria. Furthermore, the machines should be built to a standard such that maintenance can be kept at a minimum. Appropriate legal requirements, such as success in adequate trial period and safety standards, must be met in order to ensure this. Usability is also a significant factor, with trained technicians being needed to operate the machinery. This can be measured in the form of keeping records of successful diagnosis and occurrence of errors, which allow for statistics to be assembled and determine the process of rates of this technology. Data security is also an additional feature that must be considered, as solid-state storage is intended to be used. The cloud to which images are processed and uploaded must be secure and compatible across facilities. Security features that must be considered must include access and privacy of applications by authorized staff and monitoring of platforms.
Due to the radioactive substances that will be used in the fusion technology, environmental factors must be considered. Radioactive waste can remain radioactive and dangerous for thousands of years, and as such, considerations into the handling, transportation, storage, and disposal of the radioactive waste is key. Additionally, energy efficiency is also an important environmental consideration. Different designs will differ in their levels of energy usage. With increased efficiency, less resources will be wasted for single scans. The proposed multi-resolution fusion was chosen to combat this waste. Sustainability is another pertinent issue. Increased sustainability will lead to the machine being replaced less and means that less materials and service hours will be needed overall. A sociological benefit of medical imaging fusion is the increased resolution and clarity of the scans. This increased resolution and clarity decreases the quantity of misdiagnoses. There are, however, concerns that the additional time and cost for a single scan may outweigh the benefits of a misdiagnosis. As such, considerations should be made to the cost and time usage versus accuracy, ensuring that it is worthwhile. This must be assessed separately for individual regions. Through the distribution of these machines, a greater number of Australians will have access to high-end medical technology that may not otherwise be available to them. Additionally, this design will save money for the Australian government and its healthcare sector, namely radiology clinics across Australia. Legal and ethical considerations are important to ensure that no illegal actions are undertaken over the course of the project. Understanding the legalities enables us to develop a design by eliminating non-viable options that may not fit with Australia's legal regulations. The radiation produced by multi-resolution fusion and spatial fusion must be closely monitored. it is important to refer to the Australian Radiation Protection and Nuclear Safety Act from 1998 that is currently in place. Radiation levels can be measured and monitored using a Geiger counter. The Australian Radiation Protection and Nuclear Safety Act from 1998 refers to the licence that is required to install and operate the final design. Additionally, it refers to the nuclear waste storage requirements. This licence will be a definite requirement for the implementation of the design, and proper verification must be done to ensure that everything is in line with any regulations. The design must also be ethical in its implementation and utilisation. The proposed design should not produce any more radioactivity than is absolutely necessary. Patient care is a top priority in this design, and thus no shortcuts should be taken that could cause any unnecessary harm to both the patient and the user. Although the radiation dose may meet legal requirements, consideration should be made as to whether it would be even lower than that to further minimise patient risk. Finally, the amount of information provided by the machine should be sufficient to ensure the image produced is clear and informative enough to actually benefit patient outcomes.
To conclude, issues relating to missed and incorrect diagnoses can be minimised by incorporating multimodal imaging technologies into the medical industry, increasing the overall resolution and providing more comprehensive, accurate images. The development of this new technology will involve and benefit many stakeholders, including the Australian government, businesses, patients, and hospital workers. Overall, the presence of this new technology in facilities across Australia will promote an overall improvement in the health of patients due to increased diagnostic rates and improved treatment options. The benefits of medical imaging fusion lead to exciting prospects for our healthcare system and populations alike, demonstrating that this is a promising area for investment.